Our final lecture is going to focus on the carbon cycle and the environment. So first, what are the different components of the carbon cycle? The carbon cycle is one of the many cycles that characterize Earth systems, but we're going to focus on the carbon cycle because it has massive impacts in all of Earth's spheres. So what do I mean by Earth's spheres? We have the atmosphere, the hydrosphere, the lithosphere, the biosphere, and the cryosphere. Okay. Those are a lot of terms, but of course, as I love to do, we can break them down to understand explicitly what they mean. So we all know what the atmosphere is. It is the air around us and all of the gases above the ground. And that is pictured in this diagram up here. Next, we have the hydrosphere, and just as it sounds, it has to do with hydro, so water. That is all of the reservoirs of water on our planet. So not only does the hydrosphere include the big marine environment, the oceans, it also includes rivers, lakes, and streams, freshwater environments. Next, we have the lithosphere, litho meaning rock. And the lithosphere includes everything below your feet, whether it's solid rock, soil, sediment, or even fossil fuels that are buried deep within the earth. That is the lithosphere. Next, we have the biosphere. That is anything that is living. So you and me, we are components of the biosphere, but so are trees, things involved in agriculture, and also wild plants and animals. And next, finally, something that doesn't get nearly as much as attention as it deserves is the cryosphere. Cryo meaning cold. The cryosphere is the frozen solid pieces of Earth, like permafrost environments or sea ice, as well as something called deep methane hydrates, which are frozen molecules of methane that happen deep, deep underwater at the seabed. So what are some reservoirs of carbon? What do these actually look like in terms of numbers of how much carbon is stored in each of these Earth spheres? So we have multiple different reservoirs, of course, all of them characterized by different amounts of carbon that they contain and how much is moved or fluxed between those reservoirs. Now, I won't get into the nitty-gritty of these tables, but I do want you to recognize that the vast majority of carbon that is stored on Earth is actually stored in Earth. It's stored in the form of rocks in our lithosphere here. So what about these other reservoirs? What about the biosphere and the hydrosphere? So the biosphere and hydrosphere really interact with each other in terms of surface ocean productivity or photosynthesis that happens at the ocean surface. So we'll dig into that here, talking about the photosynthesis respiration cycle. This cycle mediates a whole lot of carbon movement in the ocean, as well as facilitates that carbon movement between the ocean and the terrestrial ecosystems on Earth. So let's take a look at the key interlocking components that characterize the photosynthesis respiration cycle. So we all remember what photosynthesis is. Simply, it is the fixation of inorganic carbon to organic carbon. So photosynthetic organisms like phytoplankton in our open oceans, they take carbon dioxide from the atmosphere, pair it with water, and fix it into CH2O, or a simple sugar, plus oxygen. That is photosynthesis. Now the flip side of this coin, or the other side of the cycle, when we reverse that, that organic matter is respired to be turned back into CO2 and water. So this is what we mean by the photosynthesis respiration cycle. This happens very rapidly in our surface oceans. We have the ingassing of carbon dioxide moving from the atmosphere to the hydrosphere. Phytoplankton are going to photosynthesize, turning that inorganic CO2 into organic matter. Some of that organic matter, some of the phytoplankton, they die and they settle into the seabed here. And so there's a fraction of dead matter or organic carbon in the form of bodies of photosynthetic organisms that are actually trapped in the seabed and become buried for hundreds of thousands of years, sequestering that carbon from being able to be put into the photosynthesis respiration cycle. So some of that carbon is removed from the cycle, but some of it persists in the cycle. And so therefore we have these consumers who are going to perform respiration, turning that organic carbon in the form of photosynthetic bodies into CO2 and nutrients. And that CO2 then can be outgassed to the atmosphere. So why do we care about the carbon cycle so much? It is because of the greenhouse effect and its direct implications for climate change. Now we have to go back to this idea of the difference between climate and weather. Some people conflate these two and they don't understand that there is an interaction between weather and climate, but they are two distinct things. So weather is what you get. These are conditions over a short period of time in the atmosphere. And weather can change, as we know in East Tennessee, on a scale of hours or even minutes. And so an example of this is on Saturday, it might be storming, but on Sunday, the very next day, it's sunny outside. So weather is what you get. Climate, on the other hand, is what you expect. And this is how the atmosphere behaves over a long period of time and space. This has to do with where you're situated on the globe, if you're next to a coastline or if you're landlocked, and what historically has been the pattern in your environment. This is wrapped up by average regional weather patterns over decades. And we can look at the different time scales that climate encapsulates. We have going from hours, days, and months. Those are typically considered weather variations. Like, is it raining today? Or on the count of days, is it a cyclone season? Is it your dry season? Is it a wet season? On the other hand, once we get into the realm of several tens of months, years to decades, then we start talking about climate variability. Okay, it's not full-blown climate change territory, but climate variability. This has to do with things like El Nino and the Southern Oscillation ENSO events, where you will have these decadal patterns of really intense precipitation or really dry periods. But then once we get to talking about changes over the course of centuries or hundreds of centuries, well past our lifetime, we then get into the territory of global warming, sea level rise, the rise in average global temperatures, and ocean acidification. Okay, so these climate change forcings are pretty wrapped up in this idea of the greenhouse effect. So what is the greenhouse effect? You all have probably heard of this before, and the greenhouse effect is something that has kept life thriving on Earth for millennia. It's the reason why we have so many plants at the equator, for example, such rich biodiversity at the equator. But what we're dealing with now is a runaway greenhouse effect. This is something that has caused Venus, for example, to get to such extraordinarily hot temperatures because their greenhouse effect ran away. There was nothing to keep it in check or in balance. And so that is our fear on Earth, that we will have a runaway greenhouse gas effect eventually. So let's walk through the different steps of the greenhouse effect. First, we have solar radiation. Okay, solar radiation powers the entire climate system of our planet. That solar radiation penetrates our atmosphere. Some of it does get reflected back by clouds, for example, and some of it, about half of the solar radiation, is absorbed by the Earth's surface and it's warmed by it. But the crucial but is it gets bounced back out. The greenhouse effect comes in when some of the infrared radiation passes through the atmosphere, but most is actually reabsorbed or emitted back to the Earth. Okay, and this has to do with the gases that are in the atmosphere that act as causes of insulation. Okay, This is a cloud. It is composed of water vapor, and it might surprise you to hear that the most abundant greenhouse gas in our atmosphere is actually water. It does a really, really good job of radiating solar radiation back to Earth. We also have other chemical compounds that do a good job of radiating solar radiation back to Earth. We have nitrous oxide, N2O. We also, of course, have carbon dioxide, CO2. And finally, we have methane, CH4. It might also surprise you to learn that methane has a heating capacity that's about 20 to 30 times greater than CO2. So we're always talking about CO2, but we should always keep in mind that methane is a very, very powerful greenhouse gas, meaning methane has the potential to be a much more dangerous greenhouse gas in our atmosphere compared to carbon dioxide. But let's focus on carbon dioxide because this is what we have much better long-term measurements of. And this is something called the Keeling curve. Now I'll just orient you to what this is. This is showing years along the x-axis from 1960 to the year 2020. It's called the Keeling curve because the scientist Dr. Keeling in the 1960s set up an observatory for carbon dioxide at Mauna Loa Observatory on Hawaii. There is a YouTube video for you to watch about how that got set up, but what this is showing is the monthly atmospheric CO2 concentrations in parts per million on the y-axis. So here, when observations started to be recorded, we were, about 300 ppm or so. You'll notice that we have this oscillation of going up and down, up and down, up and down. That has to do with seasonal variability, with peaks in the spring and troughs in the fall. But overall, by and large, when you take a step back, you see that clearly there's a rapid increase in the amount of CO2 that is measured from this observatory. We can do direct comparisons of year-to-year variation, and this is a screenshot that I took of the CO2 concentration this year compared to last year. So now, October 2020, we're at 411 ppm. This time last year, we were at 408. So from day to day, we might have some variability, but overall, by and large, we see that it's increasing, and it's increasing at a rapid pace. So what does this mean for temperatures? Okay, we understand that higher CO2 indicates hotter temperatures, and that all has to do with the greenhouse effect. We can look at temperature anomalies. And the term temperature anomaly simply means a departure from a reference value or a long-term average. A positive anomaly indicates that the observed temperature was warmer than the reference value, while a negative anomaly means that that temperature was colder than the reference value. So here we have January global land and ocean temperature anomalies that were reported by NOAA. They obtained this data using satellites to measure the temperature on Earth's surface at a lower atmosphere. And what we're seeing here is that from 1880, so the dawn of the industrial period, all the way through 2020, we have this zero baseline here. Bars that are below the zero in blue, those represent colder temperature anomalies or negative temperature anomalies. While the red bars that are above the 0 degrees Fahrenheit, that represents positive temperature anomalies or hotter temperature anomalies. And what you can clearly see from this chart, without even having to look at it too long, is that our January global land and ocean temperature anomalies are on the rise consistently within the past few decades, which is extremely alarming if you consider what 2 degrees Fahrenheit change globally could mean for biodiversity and ocean cycling of nutrients. Now, this just speaks to the change in temperature anomalies over time. What does this look like on a geographic scale over space? Here again, we have a graph from the National Centers of Environmental Information, a governmental agency who've done a really great job of compiling this data. And what we see clearly is that the majority of the warming that's happening on our planet is happening at the North Pole, which is extremely scary. And it raises some key questions that we need to be asking. So what does this mean for the Arctic? Well, first thing is a loss in sea ice. Here we have a satellite image from NASA of the extent of long-term sea ice in the year 1984. So before many of us were even born, this is what the quote polar ice cap looked like, with the more intense white color indicating it's more permanent ice, so persisting for 4+ years. So fast forward to just a few years ago, 2016, what does this landscape of sea ice look like? It looks like this. So not only are we losing the mass of sea ice that we have, we're also losing the amount of permanent sea ice. And the Intergovernmental Panel on Climate Change has estimated that we're losing about 10% of our sea ice per decade. That's extremely scary when you think about the consequences of what that loss of sea ice means. So in losing that sea ice, this of course needs to go somewhere, right? Though the water has to go someplace after it melts. We're seeing sea level rise. And so here we have satellite data from the year 1993 to present. And this shows the height of sea ice variation in millimeters per year. And we notice that we're seeing a rate of change in about 3.3 millimeters per year. So because of that sea ice melting and it not being permanent, meaning not reoccurring year after year, that water is then going to the oceans and we're seeing our sea levels rise at a persistent rate that we can measure. So this is what's happening now. What we need to do is put this in a context of geologic time. So let's take a look at temperature throughout geologic time. And what we can do is determine past climate of the Earth by mapping the distribution of ancient coals, desert deposits, tropical soils, salt deposits, glacial material, as well as the different types of fossils of plants and animals to understand what Earth's climate looked like. So here we have present day represented at the top. Going back in time, we can see mean global temperatures, whether we were in a cold period or a warm period. And we can also do estimations on mean global precipitation. Was it more dry or was it more wet? So what we see from this data is that for the past 1 million years, CO2 concentrations did not surpass 300 parts per million. If you remember back to a couple slides ago, today we're at 411 parts per million. There has been both cold periods and warm periods on Earth. The issue is the rate of change that we are seeing now. It is very alarming because what used to take millions of years to achieve in terms of climate change, we are experiencing in mere decades. Let's go back to one of the last times it was pretty hot on Earth. We have the Paleocene-Eocene thermal maximum, or the PETM. This is when Earth's climate was much warmer than it was today, and it's widely recognized by scientists as the best geological analog for human-induced global warming that's happening right now. This period of Earth's history was about 56 million years ago. It is thought to be triggered by a volcanic eruption that released a whole bunch of carbon. We're talking 5,000 to 10,000 gigatons of carbon into the ocean and atmosphere over a period of less than 10,000 years. So we had methane hydrates at this time being unfrozen and released to the atmosphere. So not only did we have greenhouse gas emissions from volcanoes, but we also had it from the sea as well. So during this period of Earth's history, the Earth warmed about 5 to 8 degrees globally over 200,000 years. We saw massive ecosystem changes from these temperature swings. How we can recognize this is shifts in the types of plants in the fossil record. So if you go to Utah, for example, Utah has great stratigraphic records of the Paleocene-Eocene thermal maximum. So here we have a timeline in millions of years going from about 56 million years ago to 55 million years ago. Before the Paleo-Eocene thermal maximum, over here, we had a cooler climate. So before, we had relatives of dawn redwood, alder, sycamore, and walnut in the fossil record. But then, shifting to the rocks that contain evidence of the Paleocene-Eocene thermal maximum, we have things like beans, more tropical vegetation, things like pawpaw, poinsettia. These are plants that enjoy warmer temperatures more. And then after the Paleocene-Eocene thermal maximum, we again return to a cooler climate, which again, we have the same fossil assemblages flanking the Paleocene-Eocene thermal maximum. And so the big thing to remember about this period of Earth's history is that the warming that we saw then occurred over tens of thousands of years. And so what we need to ask ourselves is, what does climate change look for us? I'm going to ask you to perhaps pause the video, take some time to cogitate on that, and answer the question, how does increased atmospheric CO2 change Earth's environments? One way in which Earth's environments are actually being changed right before our eyes is with permafrost thaw. We are seeing permafrost thaw right before our eyes. Permafrost is defined as frozen ground that persists as frozen for 2 or more years. And what we're seeing is that because of this increased warming, especially in the Arctic Circle, that permanently frozen ground is then thawing, okay? What's super unfortunate about this is that many towns are built on permafrost, and the permafrost thawing has resulted in massive floods, landslides, sinking buildings, and infrastructure. So unfortunately, many of the traditional ways of life are being affected in these areas, and in some cases, towns and villages have had to be completely abandoned because of permafrost thawing. Now, not only does this affect physical infrastructure, but it also has implications for the revival of zombie microbes. So these are microorganisms who have been locked away for perhaps millions of years, but are still in that state where they can be revived once that permafrost becomes warm enough. So how this intersects with the carbon cycle is that permafrost collapse is accelerating carbon release. So not only are we unlocking those previously frozen microorganisms, but we're also unlocking the carbon that those microbes can respire, turn back into CO2, and send that CO2 into the atmosphere. I myself did some work on methanogens who convert CO2 and organic material into methane, so that more dangerous greenhouse gas. I took a look at genome sequences of methanogens living in Antarctic permafrost, and my collaborators took some permafrost from Antarctica, put it in a bottle, and they waited for about 10 years. They warmed it up and they waited about 10 years, but they were able to find viable methanogens who look like this. They're called Methanocircina, and they have several different pathways in their genome that I identified to turn organic material and inorganic carbon into that dangerous, powerful greenhouse gas of methane. What's another implication of increased carbon dioxide in the atmosphere? We also need to think about ocean acidification. This is what is turning our coral reefs white and desolate. What we mean by ocean acidification is that oceans are a really good sink for CO2. They're able to basically scrub the atmosphere of that CO2, drawing it down from the atmosphere into the ocean. But what that means is that the ocean is becoming increasingly more and more acidic. And acid does a really good number on shells that microorganisms need to live. So the ability of shells and other calcium carbonate structures like coral skeletons need a slightly higher pH to form. And unfortunately, with the drawdown of CO2 from the atmosphere, we generate carbonic acid. And carbonic acid steals carbonate that is needed by marine organisms for the formation of their shells. So once we reach a tipping point in having too much carbonic acid in the system, we then begin to have corals that are bleaching, throwing out their zooxanthellae. We also aren't able to fully form the shells of clams and our other bivalves in the ocean. Other organisms like mussels and sea urchins are directly affected. And another organism called the sea butterfly, they're called pteropods, but they're affectionately known as sea butterflies. They have these very clear and beautiful calcium carbonate skeletons. And scientists have done SEM or electron microscopy experiments to look at the direct physical effects of carbonic acid on pteropod shells. So here, we have a sea butterfly shell in normal seawater that doesn't have too much carbonic acid. It is not an acidic environment yet, but once you add enough CO2, this is what the shell looks like. So it has been completely eaten away by that carbonic acid. Extremely sad, but this is just one small example of what ocean acidification is doing to the biodiversity in our oceans. Something else we need to think about with the carbon cycle and climate change is glacial retreat. Here we have from the year about 1980 to today, the cumulative glacier mass balance in meters of water. And we can see over the decades, we have done nothing but lose glacial mass. And this means that previous extents of glacial mass have retreated so much that previous islands that were inaccessible in the Arctic, you can just take a boat right up to. So here we have an example. This is a photo of a glacier taken in 1936. And this is a photo courtesy of the Norwegian Polar Institute. And we can see from the airplane shot just how far that glacier extended into the ocean. Here we have a photo that I took in my field campaign in 2016 from an airplane over the same area, and we notice just how far that glacier has receded back. So this is, just anecdotal evidence that goes to show that we are in fact losing glacial mass. And this is a photo of me driving up to one of those areas that were previously inaccessible to, researchers that I collaborate with who have been to these areas before and now are able to access areas that used to be the front of the glacier. Now it's not. So why do we care about the Arctic so much and glacial retreat? We care so much because the Arctic is a massive sink for carbon dioxide. This is because glaciers deliver a whole lot of iron to the shelf, and photoplankton love iron. It is a key micronutrient for them to perform photosynthesis. And I just want to show you a few more photos from my field expedition in the Arctic. Here we're in Svalbard. We can clearly see this rusty red color bleeding off of the glaciers. And that's because we have this iron-rich bedrock that then melts into the oceans, feeding our photosynthetic organisms. You can take a look directly at the sediments that underlie this water, where that iron has accumulated, and it's rusty red. And this rusty red also trails icebergs that come off of the glaciers. And this is extremely important because if those glaciers retreat so much, they're not going to be an effective conduit or flow source for that iron that can stimulate primary production, that can draw CO2 out of the atmosphere. So all of this is a delicate balance, and we're still trying to understand what climate change means, especially for the Arctic ecosystems. But let's take it back to home and see the direct effects of what climate change means for us here in East Tennessee. What it means for us primarily is increased instances of flooding. And for the past 2 years, Our Februaries have been the wettest on record. We can take a look at here in February 2019 statewide precipitation ranks. Guess who was number one? Tennessee. We saw so much rain that many of us in our streets, around our homes, saw scenes that looked very much like this, completely washed away streets and roads, inaccessible at times. And we can take a look at the data and see just how wet we have been. The anomaly, so the out of the ordinary amount of rain that we saw, was about 40 inches this past year. That puts us at the number one wettest to date 36-month period we saw earlier this year. That is just wild to me. And for 2 years in a row, we have done this. We can ask scientists, why is this happening around here? And there's a hydrologist at Oak Ridge National Lab named Dr. Cow. And Dr. Cow said the main driver is air temperature warming. When it warms, it has more ability to hold moisture. And that means more fuel to the system. That's why the system has more tendency to give you an extreme event. So we can take a look at different feedbacks that either promote warming or hinder warming. Of course, we know positive feedbacks are those that promote something, so would promote warming in this case, and negative feedbacks are those feedbacks that would hinder warming. We've already discussed how clouds are a major forcing in the climate system, but they also have a role in terms of feedbacks. So clouds reflect about 1/3 of the total of sunlight that hits the Earth's atmosphere and bounces that back to space. But a warmer climate could cause more water to be held in the atmosphere. This would then lead to an increase in cloudiness and alter the amount of sunlight that reaches the surface of the Earth. Therefore, less heat would get absorbed, which could slow increased warming. So in this case, in this scenario, clouds would be seen as a negative feedback. Coupled with clouds is precipitation. Precipitation will generally increase with a warming climate due to the amount of water that's held in a warmer atmosphere. So warmer atmosphere, more clouds. But what's fascinating is that this feedback would not be the same in every geographic region on our planet. Some regions would experience more precipitation. Other regions might experience less precipitation. By and large, though, we could expect to see changes in precipitation patterns, like increased water availability, promoting plant growth. Plants will draw CO2 out of the atmosphere, thereby hindering climate change. Number 3 is the greening of forests. This goes hand in hand with the feedback of precipitation. Tree growth today removes about half of the human CO2 emissions from the atmosphere each and every year. And the ability of the oceans or forests to continue absorbing carbon dioxide may decline as the world warms, leading to faster accumulation in the atmosphere. So even though precipitation may promote plant growth, we need to have sustained forests that are protected from deforestation in order to have that lasting benefit of a green forest. And then finally is ice albedo. Okay, albedo is the reflectivity of a surface, and ice is white with a high albedo, therefore it is very reflective. By contrast, the ocean surface is dark and it absorbs heat faster. So as the atmosphere warms and sea ice melts, the darker ocean absorbs more heat, causing more ice to melt, and it makes the Earth warmer overall. So the ice albedo feedback is a very strong positive feedback that promotes warming. And unfortunately, the Intergovernmental Panel on Climate Change predicts that our Arctic is going to be sea ice free by 2030. So a lot of that ice albedo that we currently still sort of have at the North Pole is going to be completely gone. And therefore we'll have this promotion of climate warming. So at this point, you might be asking yourself, what can I do to reduce the amount of carbons that I'm outputting in the atmosphere? How do I make sure that my everyday behaviors and practices follow my environmental ethics and concern for the environment? And I do want to tell you, first of all, many of us do not have a choice in the type of society that we live in that runs primarily on fossil fuels. But what we do have control over is the money that we invest in different corporations and products and how we choose to literally navigate the world. So here in the next slide, I've just highlighted a few of the practices and behaviors that we can begin to undertake to have a more environmentally sound lifestyle. Number one, calculate your carbon footprint. This will give you a better sense of how your everyday practices and behaviors and habits contribute to your carbon footprint. Number two, eat lower on the food chain. It takes a lot of carbon, energy, and land to sustain large-scale agriculture. And as we've mentioned in previous lectures, it's actually more energy that you are gaining if you eat lower on the food chain. You could start easy by doing meatless Mondays and exploring other options in terms of meatless dinners and meals. Number three, buy less stuff. And if you have to buy, buy local, because not only are you paying for the item, you're paying for that item if it's shipped from overseas. You're paying for the emissions and carbon to get it from overseas to the United States, and then from the warehouse in the United States to your home. Number four, look for Energy Star products if you're beginning to explore appliance purchases. These are certified to be more energy efficient. Again, in line with that, try to switch your incandescent bulbs to LED bulbs. These again are more efficient. Number six, divest from fossil fuels. It is probably not something that is on your mind right now, but if you have investment accounts or retirement accounts at your work, or if this is something that your parents have, look at all of the options that you have in terms of making sure the holdings or the companies that you are investing in are having a positive impact on the environment and have a low carbon rating with Morningstar. Number seven, avoid fast fashion. Oftentimes, that t-shirt that you bought at Old Navy, I mean, are you really going to keep it for the next 10 years? Maybe, maybe not. Are you just going to throw it away? It'll end up in a landfill. Number eight, drive less. I know this is extremely difficult for many of us, especially living in an area with very few options in terms of public transportation. Number nine, if you're going to fly, try to find a nonstop flight. This actually reduces the amount of carbon output in your flight. Along the lines of flying, try to offset the carbon emissions from your flight. Many flights now, when you book your flight, you can have the option to purchase carbon credits and offset that carbon that is being emitted from the flight itself. For example, if you were flying economy round trip from New York to Los Angeles, this would produce 1.5 tons of CO2. You can have the option to pay a little extra to offset the amount of carbon that is produced. This is certainly not an exhaustive list. These are just a few examples of things that we have the power to control in our lives to make a difference on our planet for ourselves and future generations. For your participation grade this week, please go to this website, conservation.org/carbon-footprint-calculator, #/ The link will be in the PowerPoint for you, but calculate your carbon footprint and take a screenshot and upload that as the assignment for week 14.